Isaac Newton's three laws of motion state that if you have a particle of mass m that's displaced by a certain distance and within a certain interval of time, it has a well-defined velocity, which will remain constant unless an external force acts on the particle. This is the law of kinematics. If a force acts, the magnitude of it would be proportional to the rate of change of the velocity, or the acceleration, with the proportionality factor being the mass. Whenever a force acts, the action is accompanied with an equal and opposite reaction. These are the laws of dynamics. Contrary to what Newton thought, forces aren't acting at a distance but are mediated by fields. For example, the force of gravity has an associated force field, aka the gravitational field. The strength of this field can be determined from Newton's law of universal gravitation. Similarly, there is an electric field which acts on particles with non-zero net electric charge and is determined by a similar relationship. Within a piece of matter, the angular momentum or spin of particles composing it has an associated direction. If the spin directions are aligned, the piece of matter acts as a magnet and generates a magnetic field with north and south poles which lie along the direction of the spin axis. For any force field, gravitational, electric, magnetic, the effect of it changes the state of a particle, which in turn changes the state of the field. It was established by Maxwell and his four equations that with electric and magnetic fields, the change is such that a changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. Thus, the two can be unified into a single field called the electromagnetic field, and the corresponding electric and magnetic oscillations into a propagating disturbance, an electromagnetic wave. Light. Unlike an acoustical, the optical wave does not propagate through matter but through the vacuum. Changes in the gravitational field can similarly transfer energy in the form of gravitational waves, although these are of slightly different nature, as we will see shortly. In 1905, Albert Einstein proved the equivalence of acceleration and gravitation. If you imagine yourself standing in an elevator which is being accelerated upwards with acceleration g, you would not be able to distinguish this from gravity pulling you down. Another way to restate this is to say that spacetime itself is equivalent to the gravitational field. The presence of mass then does not merely warp the gravitational field around it, but warps the very fabric of the spacetime geometry itself. This is the basic insight of Einstein's general theory of relativity. During more or less the same time as the development of this theory, a new idea was proposed to explain the behavior of the electromagnetic field. It was realized that EM energy has to be transferred in discrete quantities called photons. The wave description didn't disappear, however. Instead, it was used with the photon particle description to form a new theory called quantum mechanics. In it, light and later matter were shown to move and change as waves, but be recorded as particles when they interact. Between these interactions, the motion of the wave was interpreted as the statistical evolution of the different possible states the particle can occupy. At this point, all matter and force particles can be described as fluctuations in underlying quantum fields. There is a field for the photon, the electron, and for all the fundamental particles involved in nuclear interactions. The problem with this is that matter has mass, and if it truly exists in a state of superposition, then the curvature of the space-time region around it should be in a superposition as well. Starting with John Wheeler's notion of quantum geometrodynamics and coming to our current ideas of what a true theory of quantum gravity might look like, we see that a possible approach is to quantize the spacetime continuum itself. Why? Well, first, if we consider the electromagnetic field, the strong nuclear and weak nuclear fields, we see that they're all quantum. Therefore, we should expect the gravitational field to be also. Second, we know from Einstein that the gravitational field is spacetime. Therefore, if we want to quantize gravity, we should be trying to quantize geometry itself. Loop quantum gravity is one such approach. According to loop quantum gravity, space is made of tiny pixels. These pixels represent the quanta of volume, or the Planck volume, which can be derived from the Planck length, that is, the smallest possible distance one can probe. These Planck volumes can be represented by vertices on a graph, which are connected via edges. The edges represent the quanta of area, or the Planck area. Any such graph of vertices and edges is called a spin network, and it represents the spatial geometry of a region of the gravitational field. These networks are evaluated over closed circuits or loops, hence the name, loop quantum gravity. To add the fourth dimension of time, we need to consider a succession of these spin networks collectively called a spin foam. Similar to quantum mechanics, the gravitational field has an inbuilt uncertainty to it. Only when one tries to measure a region of space by applying the corresponding area or volume operators, one obtains a definite outcome. Therefore, one can imagine that whenever matter and energy interact with spacetime at the quantum scale, the space itself is in a superposition of geometries. Additionally, the general relativistic continuum emerges only as a coarse-grained approximation of the underlying pixel structure. One of the core attributes of this theory is background independence. Standard quantum field theories are background dependent, meaning that they exist over an assumed background spacetime. General relativity, on the other hand, because it describes the geometry of spacetime itself, is background independent. Loop quantum gravity aims at being a background independent quantum field theory. One of the founders of loop quantum gravity, Carlo Rovelli, posits that space and time are relational, which allows him to explain the theory in a background independent way. This idea, although going back to the time of Leibniz and his monads, is based on Rovelli's relational interpretation of quantum mechanics, which one might say is a generalization of the informational interpretation of which I spoke of in the last video. According to the interpretation, all values of variables are relational, or are always defined with respect to some system, the same way in special relativity one defines velocities relative to a particular inertial frame of reference. Thus, any point in space is defined in terms of its relation to any other point, and any moment of time is defined in terms of its relation to any other moment. As you can see, with this approach, an absolute background spacetime structure becomes needless. Loop quantum gravity is simply one possible theory of everything, with its most prominent competitor being string theory. We might have to wait for more predictions to be made, and more importantly, experiments to be performed which confirm those predictions. With that said, I suspect that in the coming decade, approaches which are at least partially based on Wheeler's quantum geometrodynamics will play a major role in the unification of both general relativity and quantum field theory.